Hello, welcome to the Bakwas channel for self-paced tutorials on robotics. This presentation demonstrates the use of Python's scripts to control the RoboMaster Tello Talent drone, which is available from DJI based on the Tello EDU drone by Rise Robotics. Just a quick introduction to operating the drone with a Python script. In this simple demonstration, the drone flies along a simple rectangular path. The key movements are strafe, sideways, rotate, forward, backward, and a flip for a flourish before landing. Some of the other commands, including video streaming, have been omitted from this demonstration to keep the performance at a very. This tutorial uses the Software Development Kit version 3.0. The SDK is packaged with the firmware. Should there be a future upgrade to the SDK, then simply uploading the firmware to the Tello drone will ensure that one is using the latest and greatest from Rise Robotics or DJI. Using the SDK, it is simply a matter of sending a command request to the drone and optionally evaluating the response, especially if there are errors in processing the command. This tutorial is limited to using Python for the drone. Other programming interfaces, notably C or C++, will be explored in later tutorials. The two basic ways to use Python with the Tello drone are: write the commands in the Python script and run the script. Write the commands in a data file and use a Python script to read each record and send it to the drone. This tutorial will illustrate both methods. Once command processing is initiated, the drone will send telemetry data at regular intervals. Of course, user-developed Python scripts can leverage other Python packages such as OpenCV and TensorFlow Lite to provide more advanced operations with the drone. These extensions are beyond the scope of this tutorial, but definitely within the scope of future tutorials. The next few slides will review the key characteristics of the Tello Software Development Kit. The sections are architecture, connectivity, commands, and safety. The user can send commands to the Tello drone from a mobile app, a notebook or laptop, a desktop. While we will explore a physical connection to the Tello drone's hat in a future tutorial, this presentation is limited to using Wi-Fi connectivity from the three classes of devices listed in the slide to communicate with the drone. For the purposes of programming exercises, these devices are considered to represent a client instance while the Tello drone acts as the server. In other words, the programs will use the classic client-server model in the Python scripts. The data communication between the client and the server in our current exercises relies on the User Datagram Protocol, or UDP. This protocol is a connectionless protocol that is used for sending datagrams over an Internet Protocol network. UDP is a simple and efficient protocol that is often used for applications where speed is more important than reliability, such as streaming media and video games. Connectionless means no handshake is required to establish the communication. Just fire and forget, as the saying goes. UDP does not guarantee the delivery of the datagrams, and it does not provide any error correction. This means some datagrams may be lost or corrupted during transmission. However, UDP is still a very useful protocol for many applications because it is very fast and efficient. Here are some of the key features of UDP. Connectionless. UDP does not establish a connection between the sender and receiver before sending data. This makes UDP faster than connection-oriented protocols such as TCP. Unreliable. UDP does not guarantee the delivery of datagrams. This means that some datagrams may be lost or corrupted during transmission. Efficient. UDP is very efficient protocol that uses very little overhead. This makes UDP ideal for applications where speed is important. UDP is commonly used to control drones because it is fast and efficient, does not need a handshake prior to request submission. Simple protocol, easy to understand and to troubleshoot. Please remember that UDP stands for User Datagram Protocol, even though it is often referred to as Unreliable Data Protocol in jest. The activity diagram shows that the UDP sender first creates a UDP datagram. It then sends the UDP datagram as a request to the UDP receiver. The UDP receiver then receives the UDP datagram and validates it. If the UDP datagram is valid, the UDP receiver processes it. The UDP receiver may return a response, but it is not mandatory. The UDP protocol is often used for real-time applications. This is because UDP is a connectionless protocol, which means that it does not require a connection to be established before data is sent. This makes UDP very efficient for real-time applications where any delay in data transmission can impact the quality of the experience. The UDP datagram contains the following information: source port, the port number of the UDP sender; destination port, the port number of the UDP receiver; length, the length of the UDP datagram including the header and the data; checksum. A checksum is used to verify the integrity of the UDP datagram. Data, the data to be sent. For our current situation, the request payload data is the command to the drone, which is the destination. The data from the drone to the sender is the response. The UDP sender instantiates a socket with IP address and port. The UDP receiver instantiates a socket too. The connect method at the client binds the socket connection at the server end. The send-to method sends the request to the drone, which uses the receive form method to process the request. The drone then uses its send-to method to send a response, which the client processes with its receive from method. When the client has completed all transactions at its end and is ready to end further processing, it uses the close method to terminate all socket bindings. Although there are two parties, the client and the server, in any UDP communication, this tutorial focuses on developing only the client side of the Python script. The initialization step is to instantiate a UDP socket and to bind it to the IP address and port. The second step is to send the request to the server. The third step is to process any response from the server. In the case of the Tello, some time period must be granted to it to complete the requested operation. This time period is set by the delay function, which pauses the script for the specified period. It does not communicate with the server during this period. Finally, when all operations are complete, the socket is closed. Steps 2 and 3 may be repeated as many times as necessary to complete the assignments to the drone. When the Tello is switched on, it is initialized as a server with default settings for IP address and port number. When the client program, the Python script, is launched, it binds the socket with specified IP addresses and port settings for the drone and itself. This step is referred to as initialization, and it is performed only once. The next step sends command requests to the Tello. A delay period is required to let the Tello complete command operations. The delay essentially pauses the running of the script. The Tello will send a response message for each command it receives. It is up to the client that is running the Python script to process these responses. Once the Tello is in command mode, it will send telemetry data to the client at regular intervals. This data can be simply logged or processed for flight control operations. There are three basic types of Python scripts illustrated in this tutorial: hard-coded commands, asynchronous response processing, and command file processing. In the hard-coded method, all the commands are written in the Python script. For a different set of commands, the script has to be edited. This is a major disadvantage of this method. The Tello sends responses. The client may not be able to wait for each response. Some of the responses are actually unsolicited requests from the Tello, such as telemetry data. Therefore, it is more efficient to process the responses asynchronously. Finally, instead of changing the Python script to implement a different set of commands, it is more efficient to make the Python script read the commands from an external text file and send these commands to the Tello. The UDP datagram contains the following information: source or sender data consisting of IP address and port number, the destination or receiver data consisting of IP address and port number, the length of the UDP datagram including the header and the data, a checksum to verify the integrity of the UDP datagram, and of course the data to be sent. In this slide, the source IP address and port have been highlighted in red. The ASCII and hexadecimal interpretation of the binary stream is highlighted. The entire telemetry is highlighted in a different color for the hexadecimal and ASCII interpretation of the binary stream in the UDP datagram. Let us examine the telemetry message in the next few slides. The telemetry message, as converted to ASCII representation, is shown on this slide. The fields in the message are a paired combination of keyword and value. The keyword and value are separated by a colon character. Each field is delimited by a semicolon character. The message is terminated by a pair of carriage return and line feed characters, which is the universal convention for an end of record delimiter. For logging purposes, it is very simple to convert the message in a JSON format for dumping into a transactional database. For control algorithm purposes, the message can be split into individual fields that are then used in control calculations. This slide lists the key fields that are applicable for the mission pad flights. The data readouts are relative to mission pads. These fields will contain valid information only if the mission pads are enabled for detection. Otherwise, the values are flagged for administrative purposes. This tutorial is not demonstrating mission pads, and therefore further examination of these fields is beyond the current scope. Pitch, roll, and yaw are fundamental readings to control the flight of the drone. Pitch is the rotation of an object around its lateral axis. This is the axis that runs from front to back. When an object pitches up, its nose or front end rises. When an object pitches down, its tail or back end rises. Roll is the rotation of an object around its longitudinal axis. This is the axis that runs from side to side. When an object rolls to the left, its left side moves up and its right side moves down. When an object rolls to the right, its right side moves up and its left side moves down. Yaw is the rotation of an object around its vertical axis. This is the axis that runs from top to bottom. When an object yaws to the left, its left side moves forward and its right side moves backward. When an object yaws to the right, its right side moves forward and its left side moves backward. The velocity vector of the drone can be cast in the three axes of a Cartesian coordinate system. This data is used to calculate the trajectory of the drone. Vgx is the x component of the velocity. Vgy is the y component of the velocity. Vgz is the z component of the velocity. These data can be used in mathematical models to control the altitude, position, or velocity of the drone. The drone can ascend or descend based on z-axis speed. Velocity control based on z-axis speed is useful in hovering or precision landing. The drone can move forward, backward, left, or right based on its x and y axes speeds that control the pitch and roll angles. In a future tutorial, the use of these fields for altitude control in a swarm movement will be illustrated. These fields provide supplementary data to ensure efficient flight operations for the drone. The maximum running time of the drone is for a standard battery that has been published by the manufacturer. Using this data in conjunction with the remaining battery capacity can provide better support in user-developed applications for the drone. The drone dissipates heat proportional to its size, but nevertheless one must take precautions not to exceed the manufacturer's guidance. The temperature values provide some assistance in this matter. Although it is discouraged, but the true appeal of a general-purpose drone is outdoors. The time of flight distance and barometric height are useful parameters to ensure a safe flight. Acceleration is the change in speed over time. Using acceleration to control the drone permits more precise maneuvers for altitude, position, and velocity. The SDK provides axial component values for acceleration for use in user-developed applications. A controller for a drone that uses axial acceleration to maintain an altitude trajectory might work as follows. The controller measures the drone's current altitude. The controller compares the current altitude to the desired altitude. The controller calculates the desired axial acceleration based on the differences between the current and the desired altitudes. The controller commands the drone's motors to produce the desired acceleration. This process is repeated continuously to ensure that the drone follows the desired trajectory. Let us review the essential phases in controlling the drone using a very simple Python script. One cannot fly a drone in a simpler mode than takeoff and land. Takeoff is optional, but the landing is mandatory. The source script shown here has 5 basic sections: essentials, definitions, initialization, operations, and tidy up. These sections illustrate key elements of the script with the simplest possible examples. First, import the 2 required packages: socket library for the data communications between the client and the Tello drone, and time library for the sleep function to suspend the script while the drone completes a command. Second, set the IP addresses and port settings for the data communications. The IP address of the Tello by default is 192.168.10.1, and it uses port 8889 to receive the commands from the client. The IP address of the client, as assigned by the Tello SDK, is 192.168.10.2, and it uses port 8890. Third, bind the address and port pair for each endpoint of the data communications by initializing a socket. Fourth, since UDP data communications does not require a prior handshake, it is not necessary to establish a connection prior to transmission. The messages are connectionless. These messages can be sent right away. So we send the first command, which itself is the string command from the client to the Tello. This request from the client to the Tello sets the latter in the mode to receive further commands from the client. Some finer points regarding the subsequent response will be discussed later. For now, given the simple operations, let us assume that the client does not process any response or request from the Tello. Immediately after sending the initial command, a second message is sent by the client to the Tello to request a takeoff operation. Since the Tello requires some time to complete this operation, the script is paused with a sleep command for 7 seconds. It takes approximately 6 seconds, as will be shown in the logs, to reach the default height. After the sleep period of 7 seconds has lapsed, the client sends the land command to the Tello. The logs indicate that this operation is completed in approximately 3 seconds, but the example code here uses a sleep period of 5 seconds for safety reasons. Since there is no need to close any connections for UDP data communications, the script concludes with a sign-off message for the user's benefit. Please understand that the purpose of this script is to illustrate the most fundamental client to Tello communications. Apart from the learning purposes of the first script, this style of communications between client and drone using hard code instructions is not very practical, except for very simple short tasks. It is always better to drive the flight of the drone using an external text file as the repository for the commands. In this manner, the Python program will not require changes whenever there is a need to tweak the flight plan. Only the data file will change, and one can have many data files without having to rewrite the Python program. In practice, for a pre-planned flight, the commands would be saved in an external text file and read by the script. We will demonstrate these use cases shortly. Once the Tello is placed to receive commands, it takes advantage of the UDP commands to periodically send data to the client. In the current script, these messages are totally ignored. In fact, the script doesn't even process the response message from the Tello. This message is normally the string OK, as will be demonstrated later. The Tello will send telemetry data to the client at regular intervals. This data can be processed by the client to perform flight control or process sensor readings. While the basic Tello telemetry has many important values regarding the Tello, the use of the hat on the Tello Talent drone can extend the data acquisition to another level. Again, there are future tutorials planned to demonstrate this feature. In this section, we will look at the data communications packets exchanged between the client and the Tello drone. As you can see in this simple code snippet, we have initialized the address and bound it to a socket that we then let the Tello drone know that we are out to send commands. These commands are very simple in this demo. It's the command to put the Tello in command mode, and then a takeoff command, followed by a delay that is not sent to the drone, and then finally the land command, and we allow a few seconds for that to be completed. That, in essence, is the nature of packets that are sent from the client to the Tello. And as you can see on the screen, the Tello responds with an OK when it is sent the command string. And then we send the takeoff command, and the Tello responds with an OK immediately. And we have to let the Tello then complete that operation. So we have a delay of 5 seconds where we don't send anything to the Tello because the Python script is paused. After 5 seconds, we assume that the Tello has taken off. We send the land command, and the Tello responds with an OK, and we give it about a few seconds for the Tello to land. And at that point, the script concludes. So let's look at the packets going down the wire, and we're basically looking at the network data communication packets between the client and the Tello. As you know, the Tello's address is 192.168.10.1, and the client's address is 192.168.10.2. So the source and destination matter. When the client is sending the data, as in this case here, it's 192.168.10.2 as the source, and it is going to 192.168.10.1. You can see while these things are happening, and in the previous example we gave you, we did not look at all the packages, the request responses from the drone. The drone continuously, at every tenth of a second, keeps sending telemetry. And these are the packets that are coming from 192.168.10.1 to 192.168.10.2 and has all the full telemetry information. Of course, here we send the command, and immediately after we send the command, we send the information, get the information back from the drone saying OK, and we send the takeoff command after that. And as you can see here, we've sent the takeoff command. And after sending the takeoff command, we also get an OK back, and the Tello begins to rise. And while it's doing that, it is still continuously sending us telemetry information. So as you can see here, 1, 2, 3, 4, 5 packets of the telemetry information is sent, and perhaps more because we didn't capture all the packets, consisting of basic telemetry while it is taking off and trying to reach a steady height. After that operation is complete, Python client is not sending any data to the Tello drone, and the Tello drone then receives the land command eventually and concludes the flight by landing securely. I hope you understand that this is a little bit of overkill for the beginner, but to understand that there is continuous telemetry is what I want to show you here. 192.168.10.1 and sending it to the client. And the whole series on the right hand side you can see is the telemetry information. So this is useful to process. We don't have to process it in this demo, but when you are trying flight control maneuvers, it is very important to read this information and take corrective action or flight control action as the case may be. Let us examine the processing of the responses from the Tello. As mentioned previously, User Datagram Protocol (UDP) is a connectionless protocol. No prior handshake between the endpoints of the data communication pipeline is required to send a request or to receive a response. Here is a code snippet to illustrate the concepts. A very simple series of tests are performed on the response message to route or route it for corresponding processing. The basic response is an OK string. Generally, no further action is needed for this response message. The Tello sends telemetry at periodic intervals. The response for this type of data will contain the string mid. The data can be forwarded for publishing to downstream processes, either to another server or another thread in the same script. An error response will have the string prefix error. There are three basic types of error responses: command timeout, busy, unknown command. The processing of these types of error responses will be examined in a future tutorial. Finally, if none of these matches are successful, the response is simply prefixed with a string and reported for use by the user as appropriate. Let us refine the processing of the responses from the Tello by using an asynchronous function for this purpose. First, import the async IO package that supports asynchronous methods. Skipping the interrupt handler for keyboard operations temporarily, note the commands sent to the Tello are in synchronous mode. The responses from the Tello are processed in asynchronous mode by the function receive_packet. This method is defined with the async prefix. Within the method, there is no additional requirement for asynchronous processing. In the main function, the async create underbar task method is launched to operate in the background to receive the responses from the Tello. As shown in this snippet, this section does not have to process the responses as those tasks are performed in the previously defined async method. For the limited purposes of the Tello operations, this process flow is similar to running commands from an external text file, and that is precisely the recommended method in practice. Let us refine the script further by adding some code to read the Tello commands from a file and then to send these to the Tello in the manner shown previously. In addition to the Tello commands, the command file will also have a delay command interleaved between the Tello commands to permit the Tello to complete the requested operation. This delay command is of course not sent to the Tello, but simply used to pause the script for the specified period. The sys module is imported for the file open and read functions. The name of the command file is passed as a runtime parameter. After opening access to the command text file, the records read from the file are stored in a local variable. A command with the string command is sent to Tello to set it in command mode. A task is created to run the response processing asynchronously, since it is more efficient to avoid waiting for responses for better flight control maneuvers. Of course, this asynchronous mode is really intended for future scripts and not the current simple takeoff and land script. The script then starts a loop to send the commands previously stored in a local variable to the Tello. This transmission is in the same order as the commands were read from the file. As explained previously, the delay command is not sent to the Tello but used to pause the script for the specified period. The processing of the responses from the Tello will occur asynchronously. There are 4 different response conditions. When the response string is OK, then no action is taken. When the response data contains the string mid, then it is published as telemetry data. The use of this data will depend on user requirements. When the response data is prefixed with the string error, then it is forwarded to a helper function to process the error message. For any other response message, the current action is to log it in a script terminal window. In the future, when using the hat, there may be other types of response messages. Using Professor Nicholas Wood's classic stepwise refinement methodology, the Python script examples have been improved from hard-coded statements to a simple but robust solution for basic custom operations with the Tello Talent RoboMaster drone using the Tello SDK. This tutorial provided an introduction to commands for the RoboMaster Tello Talent drone. By limiting the flight to the simplest takeoff and land scenario, the programming methods were explored in a stepwise manner. Several Python scripts were illustrated. The data communication from the client to the drone was illustrated with client-side Python scripts. There will be more tutorials on extending the programming techniques for other commands and third-party package libraries. That's all, folks. Please provide feedback in any which way you can. And also, stay tuned for the next tutorial in this series. This presentation was prepared with assistance as noted on the slide. My apologies if I have unintentionally or inadvertently omitted anyone or any resource. A very big thank you to y'all. Come back to the channel soon.